Now we're at the third of the 5 segments. This one's about how to work with the law of refraction. This particular law has another name as well, named for the scientist who first put it into mathematical form. It's also called Snell's law, S-N-E-L-L. So I may refer to it by either name. This particular mathematical relationship is used to find what happens when light passes from one medium to another and changes the angle at which it enters into the new medium. So let's draw a diagram. It will help us to understand what's going on better. You also will want to put this in your foldable. So I'll make the two media yellow and pink because these are pretty bright colors. It'll show up a little bit better. We would use this particular equation whenever light is passing from one type of material to another, for instance from air into water, or from diamond into some other substance. It's often air is one of them, but it doesn't have to be. It could be diamond into water, for instance. It's a nice colorful diagram here. Just think of these two colorful rectangles as representing the two media. I'll label them as such. This will be medium 1, and this will be medium 2. Each medium has its own index of refraction, so I'll put N1 here, N2 there. And again, just as before, we need to draw in a normal to the surface, normal to the boundary which these two substances contact. There's a right angle there. Okay, so we have, as before, an incident ray. This is just like what we had with reflection. We'll call this theta 1 instead of theta I this time for the angle of incidence. But rather than looking at the reflection, there probably will be one, we're going to focus on the refraction. We're going to send this light ray on through into the new medium, and notice that it doesn't follow the original direction. In this case, it looks like it's bending toward the normal. I'll talk more about that in a little bit. Here is our refracted ray. And this is our refracted angle, theta 2. So it's a pretty complex diagram, but it's one that's worth taking the time to understand well. If we look at our equation up here, we see that Snell's law, or the law of refraction, states that the product of the index of refraction and the sine of the incident angle will equal the product of the index of refraction in the refracted medium multiplied by the sine of the refracted angle. So it's still a fairly simple relationship, but it's going to require use of trigonometry, and as such, be sure that your calculator's mode is in degrees. If it's not, you will not get the right answer. So now let's attempt the problem that's described right here. We have light passing from glass into air. I'm going to use green for glass and light blue for air. You don't have to use color when you're doing these problems, but I think it helps to visualize what's going on for you while you're watching me do this. And so I'm going to take advantage of the full functionality of the smart board here. So from glass, let's see, let's make sure we're getting the blue here. That's it. To air. Sky blue. Okay. This right here is the border between the two media. This is where the refraction occurs, the change in direction. Let's go ahead and also indicate the normal. Should always draw in the normal, whether or not you use any color. Let's draw our incident and refracted rays as well. incident ray is coming in at an angle of 18 degrees. Sometimes hard to tell from the wording, but if you look at it, if it asks you to find the angle of refraction, the other angle must therefore be the angle of incidence. And we'll find out in a little bit that this actually gets bent away from the normal. And I'll tell you a little bit more about how you can predict that once we've done the calculation. So here's our unknown angle of refraction, theta 2. Let's go ahead and label what each of these media is. Okay, so we have glass up here with an index of refraction N1 equaling 1.55. That's a given up here, right there. And air is the second medium. Air has an index of refraction of 1.00. Very close to what it would be if it were empty space. We're going to need these three values in order to find the fourth. So let's go ahead and do that. N1 sine theta 1 equals N2 sine theta 2. We know the values for N1 theta 1 and N2. So we're solving for theta 2. Let me go ahead and isolate sine theta 2. It's going to be N1 sine theta 1 divided by N2. Sine theta 2 is therefore going to equal 1.55 times the sine of 18 degrees divided by 1.00. And if you work out what that is in the calculator, which I'm about to do, make sure your calculator is in degrees. You come up with a value of 0.4790, so 4 significant figures. We're not finished yet. In order to find what the angle is, we need to take the inverse sine. Let me switch over to this column here. So if sine of theta 2 is equal to 0.4790, then theta 2 is going to be the inverse sine of that. And if you work out what that is, it comes out to be 28.6 degrees. Lo and behold, 28.6 degrees is bigger than the 18 at which it came in. So it did bend away from the normal. Now, how did I know that, apart from the fact that I probably worked this out ahead of time? Well, I could have predicted it by looking at what happens with the n values. When the n values get smaller, as they do here, the angles are going to get larger, and vice versa. If I look over here at this other drawing that I have, I see that the angle got smaller, it got bent toward the normal. So I could infer, without even knowing anything about the values in this problem, that n1 in this case has to be the smaller value. It has to go n1 smaller to n2 larger in order to have the opposite happen with the angle going from a larger value to a smaller one. We'll be emphasizing that in the days to come, but I just thought I would go ahead and point that out to you now. So why don't you give this some practice? The problems that I recommend for you are numbers 2, 7, and 8. And if you look at numbers 24 and 26 in the concept questions, there's some further material there to consider in relationship to the law of refraction. Finally, problem number 14 actually involves both the law of refraction and calculating something to do with the index of refraction. So why don't you give those a try? This ought to keep you pretty busy for a little while. And if you have time, then you can move on to the next 2 video segments.